This is video 17 in the lecture on the design of reinforced concrete beams. This lecture deals with cross-sections loaded with eccentric applied compression in domain 3. This is where compression is dominant. Consider a rectangular section with a total depth of h and an optimum depth of an effective depth of d. Then if we look at the strain diagrams in domain 3, we will see that the depth of the neutral axis is always larger than the total depth of the beam, so the whole section is in compression. You can see it on this diagram. We also see that the pivot point is situated around epsilon C2, and it's the crossing between the plane epsilon C2 constant and epsilon CU3 with and the other point 0. And when those two lines are crossing, that is our pivot point for the domain 3. We have 4 unknown strains. The strain of the concrete at the top and the bottom of the section, and the strain in the reinforcement on top and on bottom. What we will do now is to express the 4 unknown strains in function of the depth of the neutral axis. In the sense of we will use Ct, which is x divided by h. Also, we will calculate by integration the filling coefficient and the point of gravity delta G. Those are the 4 unknown strains, and we've put them in relation to the known strain epsilon C2 and epsilon CU2 and on the depth of the neutral axis. The filling coefficient is found by integration and is a function of C2. When you make a graph on the x-axis, it's Ct, and on the y-axis, it's Psi, in the function of Ct. Then we will see that on the left border of domain 3, then Ct is 1, and then the whole parabolic and rectangular area of the concrete stress block is developed. So we know that then the filling coefficient is 0.81. And if you take Ct is 1 in this expression, you find also 0.81. So this is okay. At the other border of the domain 3, then Ct will go to infinity, and then you will see on the graph that Ct will be 1. You can see this because this is going to 0 and this is 1. So this is quite logic also, because the filling coefficient of a rectangular stress block is by definition 1. This is only valid for concrete quality smaller or equal to C50-60. The point of gravity in function of Ct is also found by integration. And if you look at the graph, then we will see that for the left border, when Ct is 1, then if you calculate this, then you find 0.416, which is the expected value. And if you go to the right hand side border, then we see when Ct is going to infinity, that delta G is 0.5. This is also logic because the point of gravity of a rectangular section is 0.5 times the depth of the section. We have the geometry, the strains, the stresses, the forces, and then the external forces. The external force, the bending moment is replaced by an eccentrically placed normal force. Because this is domain 3, the E0 will always be smaller than the E2 because of the compression which is dominant. If you take a translation equilibrium, then the external force equals the internal forces, and you will see that this is the compression force in the steel, and this is the compression force in the concrete. But you see that we are now, because the section which is in compression is the whole section, instead of X we use H, because if you use X, there is a portion which is falling out of the section, which does not belong to the section, so it should be wrong. So that's why X cannot be smaller than H, so H is the maximum value. So the total compressive force is of course the total height of the section times the width of the section and times FCD. But if we do that, we have a little bit too much, so we will multiply with the filling coefficient. So it's CBH FCD. Rotation equilibrium around the most compressed reinforcement. So rotation equilibrium around this point here, or around this point here. Then you see that ND times E2, ND times E2 must be equal to the concrete compressive force times its lever arm plus the reinforcement times its lever arm. Again, take care you use H and not X. The protocol, how do we calculate now the reinforcement? You first start with the eccentricities E0 and E2. Then you have a first iteration and you assume that sigma S1, the tension in the stress in the tension reinforcement or in the least compressed reinforcement is 0. We calculate the reduced bending moment. Take care, it's h squared and not d squared. Then we look at the depth of the neutral axis with this formula. Then we calculate the filling coefficient and the coefficient of the center of gravity. And we know that the strain in reinforcement concrete is also a function of CT, so we can calculate them too. Then we calculate the stress in the reinforcement, and after that we can calculate the reinforcement area. But we have one variable too much, so there are an infinite number of combinations AS1 and AS2 that comply with the formulation. So we take the proportion of AS1 to AS2 is equal to Chi, and then we express AS2 as a function of Chi times AS1. Then we can have an expression for AS1 on the condition that we estimate first Chi, which is most of the time 1, because of the symmetrically post reinforcement. Then we compare the initial stress. We started with 0 and we have now calculated the stress in the least compressed steel. We compare it. If it's not the same in a reasonable margin, then we make a second iteration. We modify the reduced bending moment with the sigma S we found and the AS1 that we found. And then we repeat step 3 to 8 until the iteration is finalized. We have seen now the calculations in domain 2A, 2B, and 3 for eccentrically applied compression. We have seen that in each domain you have different formulas. It's therefore important to know in which domain you are. So for that you need some borders, and these are the border lines left and right, and the value of mu d at the borderline left or right. You see for domain 2A it's independent of delta t. For the others it depends on delta t. Ct we know was with this formula. If you go to the right border of domain 3, we know it is pure compression. That means that CT is infinite. That means that this term should be 0, or mu d must be 1/2 minus delta t. At eccentrically applied compression, you need to know which domain you are, and you can estimate this by comparing the initial eccentricity E0 with respect to the depth of the beam. So we will do that in a small case with a beam 600 by 300, where the reinforcement is symmetrically. And then we will look at 3 cases. With different normal forces, different bending moments, you will see that the initial eccentricity goes from high to low. And we will see that when the initial eccentricity with respect to the half of the depth of the beam is more than 1, then we are most likely in domain 2A, or we are most likely in a bending dominant situation. When it's about 0.29 and 0.1, you are in domain 2B and domain 3. So the distinction between domain 2B and 3 is not that significant. So when you start doing a calculation by hand, you start with domain 2B, you calculate mu d, and you check with the border limits if you are really in domain 2B. If not, you change it to domain 3. Let's now work those 3 cases. Let's work it out. Case X1, we start with a steel stress of 435 for the compression steel, the most compressed steel. We calculate the eccentricities, we calculate mu d. Now, if you got mu d in the first iteration, I have 0.305. You see, this is with the limits of the domain 2A, we are within those limits. So it is fine, it is okay, we are in domain 2A. Then we calculate the needed reinforcement, but this is now a doubly reinforced section where we assume in the other cases that the Chi is 1. We assume a symmetrically reinforced section. So for comparison reasons, we are also going to reinforce it symmetrically. But we don't really need the compressive reinforcement. So we will choose mu limit. It's a little trick. We will choose mu limit in such a way that the reinforcement is symmetrically. If you do so, mu limit will be 0.221, and you fill this in 0.221, and you have 600 square millimeters, and you will see then mu n is 0.221. Then we follow the procedure, and we find that the tension reinforcement is 601, so it means 3 diameter 16, bottom and top. Now we go to case number 2. In case number 2, we start with the least compressed reinforcement, and we estimate the stress into the least compressed reinforcement. We calculate the eccentricities, and we see mu d. Mu d is 0.217, and this means that we are in the domain 2B. So we continue, and we see that sigma S1 is 18. So we started with 100, this is 18. So second iteration, we use 18. Mu d, we use the corrected calculations of mu d with the stress that we had as estimate and the reinforcement that we calculated. Again, we check if we are in the right domain. It is possible, if you are not so lucky, that from this step to this step you change domain. Then you have to use other formulas. So we continue. We have now 14 as stress, and we do second iteration and a third iteration, and we find that the needed reinforcement is 598 square millimeters, or 3 diameter 16 is okay. Then we take case 3. We start with 180 Newton per square millimeter or megapascal. You can also start with 200 or with 100, but we know it will, if you start with naught, that's not right, because the whole section is in compression. So you start with a certain value, and then you will see it will be corrected. We calculate mu d. We see that mu d is 0.36, so it means that we are in domain 3. Okay, that's fine. We do the calculation and we find, as I stressed in the steel, 223. So we have the second iteration and the third and the fourth iteration, and at the end we have 600 or 599 square millimeters, or this is 3 diameters 16. But now something looks strange. Case 1, 2 and 3, they all have exactly the same reinforcement. How is it possible? The normal force and the bending moments differ enormously from each other. They are totally different, and the reinforcement stays the same. This means that if you make a graph of the normal force on the x-axis and the bending moment on the y-axis, and you take a section, a concrete section, symmetrically reinforced by, for instance, 3 diameter 16 top and bottom, you apply 1000 kilonewton compression on the section, and then you calculate what is the capacity and bending moment of this section, and then you will find something like 3200 or 320 kilonewton meter. Then you end up. If you increase the compression but 2000, then you will end up with another bending moment as a capacity, and so on. So if you plot all those different points, you have a graph. It's called an interaction diagram. So you will see that for one section with a fixed reinforcement, you have an infinite number of possibilities for normal force and bending moment acting on the section. You will also see when this curve is going up until it reaches a maximum, and then it's going down. Well, this portion is dominated by bending. It's bending dominated. When we go a little bit further, this portion here, it's compression dominated. So you can see on the graph, if you are over the hill, then you tend to go to the compression dominant. So you intend to go to the 2B domain. This is domain 3, this is 2B, and this is domain 2A. You can now calculate the needed reinforcement at eccentrically applied compression, where the compression is dominant.